Sometimes people like to use the dimensions A and B. Okay, so from here, hopefully you know the difference. Sometimes people like to adopt the AB rather than 2A, 2B. So don't be confused. Here I try to come up with the kind of the different tabulation. Again, if you would like to adopt this kind of the symbol conventions, AB like this, then this will be the corresponding numbers for the table for the tabulations. Okay, and people before sometimes ask me why they come up with the table, the numbers are different from other people. Simply is this reason. Okay, and so for this case, you can convert it. Compared to this number, the number for this one, basically that is scaling factor of 8. Corresponding to this one, that's corresponding to the scaling factor of 16. That's it, because of the scale in the dimensions. But it would be easy for me, I simply say for the problem definition, and I look up where the kind of the symbol, which one they use, and then I refer to the appropriate table, and then right away I dive into the calculation for the whatever they needed. I think that's the final thing I want to come up with to you. Good? Okay, so one final thing. I think in this slide, I have utilized the symbol here. So let me utilize this equation for illustrations. Okay, and one final note I want to I would say one final symbols I want to deliver to you. For this case, using this one, let me rewrite here. T equal to G beta and K2 A3B. And here I've been so nice to everyone here. For, you can see I use capital K2 for this scenario compared to the lowercase K2 for this scenario. I know some of you are picky and sometimes you know which K2 I'm talking about. That's my symbol convention. Hopefully you adapt it. Okay, let me start with this one. So for this case, compared to our ES331, that is fundamental mechanics material. And we have learned the angle of the twist. So basically that is this. We have a shaft, and under this kind of torsion, if we fix at the bottom here, the angle of the twist is the angle be twisted at the top surface here. That is called the angle of twist. It's TL over GJ. Okay, that is the formula we know. For this case, we see how can we do it. So let me define this one is J. And G, beta is phi over L, J. So from here you can see phi still equal to TL over GJ. The same thing. Right? By doing so, this one, we have introduced this number defined as J. What is J? J is for the polar moment of inertia. So for rectangular shaft, and how to determine the J, that is this number here. And again, for this number corresponding to is this note or whatever the K2. So skip off this one, 1/3 here, then pretty much if you like, you can use K2, okay, like this one. If you're going to adopt the previous slides, and for these dimensions, again, whatever the K2 you refer to on different aspect, again, this is the J, moment of polar moment of inertia. Compared to rectangular shaft, for circular shaft, and say of radius R, the J, try to refresh your memory, that is 2 pi R to the 4th power. So that is for circular shaft being used before. Okay, but compared to the rectangular, that is this number. Good? Okay. Good? Okay, nice.